Good morning. It is wonderful to see everybody here on February 1st. Not much is going on in the world, right? There haven't been any headlines or anything like that. So we're here for Science on Saturday. Just one quick announcement before we get started. I'm very excited about today's speaker. Um, Thank you for your patience as we had to reschedule last week's speaker. He fortunately has agreed to speak at the end of the lecture series. So we're adding March 15th as the last lecture. So we're just moving him to the end. Also, just so you know, the last few lectures we are going to have on main campus, and we have identified a auditorium on campus with a parking garage right next to it so that the walk will be very short. So we're getting those details worked out and should be able to give you all of that next week. For those of you who are online, of course, we will continue to stream live. So that's the only changes that are coming up. So thank you very much. I heard the bagels were gone earlier this time. So we keep on ordering more, you keep on eating more. And so I think the question is, do we order less because you'll eat less, or do we just double the order and see at what point we reach that double? Yeah, I hear a double. Okay, got it. So I'm delighted to have our next speaker talking about something that I think that we have all heard about at one level, which is plastic pollution. And you can see her bio here. One of the things that's really remarkable about working at both PPL and at Princeton University is the fact that amazing ideas come out of the university, come out of this laboratory. And those ideas can often become incredibly successful companies. And so today we get to learn about really the birth of one of these wonderful companies. And so would you please welcome Yidian Liu to the Science on Saturday stage. So she's been warned, as we all have, but we'll start with the three questions. So as you can see, her background is interesting. It's in architecture, actually. But the question is, when did you get first interested, I could say science or perhaps architecture?
Sure. I would say my first interaction with science is actually towards the end of my graduate degree at Princeton, because when we're looking at plastic problem, we're trying to look at it as how it is affecting the urban landscape and how it's affecting our life. And when we started to look into system to control the plastic pollution is when we actually getting scientific, which is the opposite of what architects do. Right before we started PolyGone, I was trained to do like rich people's home. I'm very good at making drawings for rich people's homes. If any of you want to do a house design, you know who to talk to. Yeah, but that is not something that would cheer me up in the night, right? I want to do something that's slightly more um, outbreaking, challenging what is most architects do and how technologies can actually advance our cities to a better place.
Wonderful. So whether it's in architecture or anything else, tell us about a teacher who had an influence on you from the time you were little to graduate school.
I'll actually say my thesis advisor at Princeton. So I picked him because we were in a seminar together, and his focus is actually um, architectural systems that impact the future of humanity. For example, we can pick subjects like data center. Some people pick like urban farming. So the subject I picked was plastic pollution. I'm curious about what systems are currently doing the recycling, sorting of the plastic waste, and how is that currently managed by especially US cities? Where do plastic waste go, and why do they end up in the environment? And is there anything else we can do to improve it? So that actually set stone for my thesis research, and that was actually prior to the foundation of the entire idea of PolyGone.
And last question, something when you're not trying to remove all plastic from our environment, something you do for fun.
I like ice skating.
Say more.
After this, I'm actually rushing to an ice skating class. I'm learning, but I really enjoy activities that's like kind of requires a lot of body control, like core muscle and
Can you
stuff.
do all the spin
And
stuff?
of course, it looks cool as well.
Thank you. And so with that, systemic solutions for microplastic pollution at PolyGone. Thank you so much.
Thank you. So first, I want to introduce PolyGone. The reason we named it PolyGone is because we're trying to convey the concept of getting rid of plastic. So PolyGone stands for plastics of all scales, but what we really trying to start with are microplastic. And why is microplastic so important for our team and what we believe for the entire world? Is because microplastic is one of the most alarming pollutants that's entering our food system and may actually impact our next generation. And research has shown that microplastic are found in all of our oceans and in more than 93% of our drinking water. So it's a very alarming number that's been even growing because the current days of plastic consumption is like still growing. So what is microplastic? Microplastic are plastic particles that are smaller than 5 millimeters in diameter. That's the general definition. But nowadays, we like to separate the concept of microplastic from nanoplastics. Nanoplastic are the microplastic particles that are smaller than 1 microns. And then those two subjects are usually studied together, but when we are doing advanced analysis, nanoplastic are looked at in a slightly more niche ways. So how severe is the microplastic problem? I want to use this bottle of water as an example. So can someone give me a guess of how much microplastic plus nanoplastic might be in this bottle of water? Just one guess. How many particles? How many 42. Okay. 1 gram? 1,000? Okay. Is actually between 90,000 to 140,000 nanoplastics. Okay, after hearing that, are you still drinking this water? And sometimes, like after you put like water in your car for like a long day, and we go back to the car, you feel like the bottle's getting soft. You open the bottle, you feel like drinking like weird taste of plastic, because you are drinking plastic. Yeah, so after knowing that, I'm like very cautious about my drinking water. And I think everyone should be more cautious about it. So what you can do is maybe start looking at home filtration systems and etc. Okay, that's the reason we want to look into microplastic. We want to find solutions so we can actually remediate the problem in a systematic way, get rid of them from our drinking waters to protect our next generation. Microplastic can cause a lot of harmful effect. So based on the clinical studies in the last few years, the amount of plastic in our body has increased, and then the sizes of microplastic has also become bigger. And microplastic are found in all of our organs, like lungs, and also blood and brain. And it also can carry between mother and kids. So the current thing is we know is that, and it has some effects for the or how our body functions, like the reactivity and then reproductivity, but we don't know what is the threshold of microplastic accumulation. But the question is, do we actually want to wait until it's too late to address this problem? And that's how we want to interfere. Currently, let's look at the system to interrupt plastic pollution as a whole. So in the rivers, when we walk by the canals, there are often those floating barriers, and you see like the organic waste, the tree trunks, leaves, and then the bigger floating plastic being captured by those systems. Those are quite effective for the larger floating plastic, but they're not really effective for plastic that are smaller than 1 millimeters, which are the ones that are actually entering the water system. And existing infrastructure, some of them can already filter microplastic. For example, reverse osmosis systems. A lot of those systems installed in our home, and then for the sanitation plants. But those systems are several millions for the larger with water treatment systems to install, and then very energy intense to operate. So we're thinking like more than 70% of the US water treatment system actually do not have the resource or the space to install like those kind of advanced systems. Can we have something that's in between, that's easier to install and that's cheaper, and then require less labor to operate? So my co-founder and I, when we were at Princeton, we're thinking, okay, that may be an interesting thing to look at a problem. So first we start looking at the sorting, aquatic plastics and plastic sorting recycling centers. And later we find out there's like no major infrastructure system that actually solve microplastic. So we kind of went outside of our department because if we're architects, what can we do, right? We talked to the people from the environmental engineering and chemistry department. And then we're like, can we actually innovate a simpler system for filtering microplastic? And that's how we met some of our early members, including Dr. Yidian Liu, who's also graduated from Princeton chemistry department. And at the beginning of our research, we presented, okay, we want to sell microplastic to our department. Our professor was like, no, you can't. This is just not a topic for architects to solve. You're not an engineer. You can't potentially propose anything. They hate it. And we're so mad and so stubborn. So we went out of the way. We not only talked to you also talked to a lot of others in the broader range of the Princeton community. And then together we filed our first patent, and we innovate a smaller system I'm going to show later. And we bring back the same idea with the authorities behind us to our university board. And they suddenly changed. They're like, this is the best idea I've ever heard. I love this. And then we won the CSIS Award and the Princeton Research Day in 2021. It gave us a lot of confidence to enter the problem following the graduation. And following graduation, my co-founder Nathaniel and I decided, okay, maybe we can actually do this as a business. So we worked on it as a moonlight project for a few months. We built our prototype, and we were very lucky to get our first investment. That's when we decided to go full-time. And now the team is around 8 to 9 people. We have a few full-time and a few part-time working together. Luckily, we're the only architects in the team, and everyone else is from a more engineering and scientific background. But we really enjoy this kind of interaction between different subjects because I can never design a lab experiment to save my life. So this is the system we innovated. It's called the artificial root filter. Why is it called artificial root filter? Because it imitates the fibrous structure of an aquatic plant root. Because we find out a lot of floating wetland systems, those like the green infrastructure, can actually capture a lot of smaller pollutants that includes microplastic. So we're like, can we actually borrow this idea from the natural system and turn that into a filter? And at the beginning, we actually thought maybe we can just use a plant root. Like we plant them everywhere, so that's how we stop microplastic, right? And then I did a small tank in my apartment, and then the plant keeps dying in my tank. And I also like consulted a lot of experts who are actually doing those floating wetlands. They're like, that may not be the best idea, especially for the US, because the climate is very different for different plants. So there's not one plant that would suit all kinds of climate. So you always have to update. Plus, a lot of animals, wildlife like to inhabit it in floating wetland, making it very hard to manage. And also there will be nutrients building around the wetland, may not be the best scenario for a lot of open water. That's why we say, okay, maybe we can make an artificial route. So it does not really function or like die like a plant root, but you can still attract microplastic. So the system is like the filter is around 8.5 inch long. The reason is that it will be interfered within the top layer of the water and then just above the water a little bit. So we also tackles the interface between the water and the air. The reason is that microplastic, most of them, except the PET plastic, are lighter than water. So they tend to float on the water surface. 80% of the plastic in the open source are in the top water column. So by inserting the filters there as a bigger array, we can actually capture a lot of plastic that pass through. And then the idea is that we're using a hydrophobic material. Microplastic, most of them are also hydrophobic. So when they pass by, they tend to be attracted by this filter. While the fish can still go around it, so it's not really interfering how the natural system works. So it's a 100% passive filter, so we do not require any like high pressure water to be forced through the filter, but it actually just sits there passively, gets the microplastic, and is so much cheaper than the reverse osmosis and those stuff. And then the image you see on the right is actually our next phase. So I'm going to talk about phase one of how the system looks like in a group, and then we could go to the phase two. So how the system work with like river is that we can create an array of the filters that kind of covers the entire cross section of like a smaller stream. And by having many of those stopping barriers, we can actually stop microplastic from entering the broader waterway. And the filter is made of silicone, so it's not really reactive and it doesn't really break in the UV light. So microplastic are tend to break in the UV light because the chemical bond is very fragile in comparison to many other materials. But silicone, it also breaks, but it does not break in endlessly into smaller particles. So by using silicone, it's actually quite a lot of material, but can still do the microplastic attraction as we wished. The performance metrics. So when we talk about microplastic, we have to separate them into different categories. So from the shape and size category, we have like foam, we have fibers, we have fragments, we have films. And then from size class, we have the one that's bigger than 1 millimeter, between 1 micron and 1 millimeter, which is 1,000 micron, and the ones below. And from the chemical perspective, we have LDPE, PP. LDPE and PP are usually the ones for our quick, like fast food when they have the food packaging. PET is like those kind of clear plastic. PVC are the ones used in our pipes. And there are also like HDPE that I'm not going to go into details here. So in our lab experiment, we convey that the system can capture up to 90% of microplastic that's introduced into a controlled flow tank that we innovated. So you can see the image there. All of those fluorescent particles are actually microplastic that we introduced to the water, and they just stick to the filter like a Christmas tree. So after the lab experience, we were like, okay, We're ready to do something in the field. And in the field, that's another story. So we did small scale projects and bigger scale projects. The first proper pilot we did is a monitoring project in Canada. So there's a very beautiful lake in Canada, and there's a group of innocent researchers, and they want to study microplastics' impact to the environment. So they find this very isolated lake, and they're dumping tons of microplastic into the lake. It's, we will clean it up after this year, so that we can understand what is the pathway of microplastic, right? Does it go to the soil? Does it go to the sediments? And what are the wildlife that's around this area? And then what are the accumulation like? So our system was put there so we can we have around 40 filters of the artificial root filter and a floating pontoon. So the system will sit there for 6 weeks. And then every week we take one filter out and then we study how much microplastic is captured, what is the curve looks like after the few weeks. And we successfully captured 520,000 microplastic within that period of time. And the second pilot is what I'm most proud of is the first microplastic removal pilot at a major water treatment plant of the Atlantic County Utility Authority. And they're a very cool group. They're already doing very innovative things in their site, such as like giant windmills and then a lot of solar panel. For a wastewater treatment plant, that's pretty impressive. We met them in a water conference, and we were like, we have this microplastic filtration prototype. Would you be interested to do a collaboration with us so we can build a pilot together? And they're very happy, accepted to this idea. So together we applied for several state and federal grants, and we were very lucky to get those opportunities to actually build this pilot. And the third one is in California. So it's a smaller system, a smaller channel, and they're also interested in trying the artificial root filter. And we designed a different wheeling system for their smaller channel. So I want to go into a little bit detail about the first wastewater treatment pilot. So you can see in this map of the facility how water are currently entering this treatment facility is actually through like a pipe here, and then we go through the primary and secondary treatment, and then the water will be gone to the pump house. After the pump house, they were supposed to be pumped into the ocean. So we are interfering at this point when the water is resting after the secondary treatment. So we are not worried about the most of the solids or the sediments that are typically in the wastewater. The water is most likely clean. And there's a channel of around 16 feet where the water comes out. And that's where we put our systems as a large array to cover the entire cross-section of the outflow. And this is what I call a basin, basically for water to rest before they pump out of the water. The ACUA facility actually serves around 200,000 residents in South New Jersey, and they also are processing around 40 million gallons of water per day. So it's a very large volume facility. We are a little bit nervous at the beginning because the size of the channel is quite large. We're thinking about something that's like smaller than that, so it's a easier to control experiment. But we have to build something really large. So this is what we did. We have 2 arrays of the filters. This is the concept. Probably it's easier to see this way. So 2 arrays of filters. Each has around 360 root filters, and we're running them as like alterations. So when one system is down, the other system will be up for cleaning. And depends on how dirty the water is, we change the frequency of the 2 system going up and down. And there are 2 external cleaning tank to clean the filters when is saturated, basically. And we currently captured around 650,000 microplastic per wash cycle. And wash cycle means, like, let's say if I'm altering every day, then that change of time is one wash cycle. And with this current frequency, we're expecting around 580 million microplastic per year. But this system is also very mechanical, requires people to still like push the button to go up and down. So the next phase, we want to make it a little bit more automatic. And on top of the main system here, we're building a educational pavilion to talk about microplastic pollutants. We want to let people know what are the sources, what are the pathways of microplastic, and then what are the existing solutions for it. So this pavilion was actually taking the form of the water pipes on site and then turning that into like a architectural language. That's when architectural skills actually is useful for the first time in this business. And we can design different sections to entertain different display objects. We have a short videos about the overall. So a big part of this project is actually procurement and construction because no one has built something like this before. And a lot of things, when we first proposed, we showed the engineering drawings to a installation firm, and they quoted us $200,000 for just putting this thing into the channel. Where that's not going to work. We didn't have that kind of grant money for you to have your workers on site for 5 days. So we reiterate the design to make it slightly easier to install, and then we change a lot of things to make it more modular and off the shelf. It actually helped us to streamline our whole design to make it more affordable to more facilities. And then we got the price down to 75K after the addition. So we saved more than 60% on the installation cost. And then the education pavilion, we can see from the photos here a little more clearly. So there's a little device inside of a hole. The idea is to have microplastic, fluorescent microplastic inside. And then when you turn on the regular light, you're not going to see the microplastic. There's also a UV light. When you turn on UV light, you see the Christmas tree of microplastic to show that microplastic is an invisible problem, but it's actually very critical. We also have different display items on the typical items in our life that contain or cause the leach of microplastic on the site. This is our grand opening day. We have around more than 100 people turn on to the grand opening. And then the system is still in Atlantic City now. We're going to have that on for the next 12 months, and we're going to build a phase 2. I have another short video here. So we do have some preliminary pilot data from this pilot. So I was talking about we have more than 600,000 microplastic per wash, And then sometimes we have very high numbers, sometimes we have lower numbers. That's because the volume of water changes. Also, the inflow and outflow weather condition are also different. So we have like an average of 600K to 650K actually. And from the type of plastic, we thought we're gonna get majority of the plastic from fibers because wastewater treatment receives a lot of water from laundromats and just urban wastewater. So we thought like clothing release a lot of fibers, that would be the main source we capture. But actually we capture majority, 92% of particles. And we have some fibers and fragments. So next step would be actually automating the system because we think that the current rhythm of how we are changing the filters are not very, can be faster, can be more frequent, but a human does not need to be there all the time. So the automated system will allow us to do the cleaning of the filters more frequently, and also you will have a sensor to move the entire system into the water channel automatically. So it captured most of the microplastic on the water surface with the fluctuation of the water. And then the operator can just go into the control room and click one button, and that's all done. So this process, we are going to apply for another grant opportunity for it this year, and then we aim to get it built by next year. So the whole vision for PolyGone is to actually tackle the key emission points of plastic that enters the water. So this is where we interface. We want to capture microplastic from rivers, lakes, water treatment plants, and their sludges. So we can interfere from multiple avenues and collect microplastics so we can remove them from our waters as a whole. Currently, we have received just about $2.5 million of grant awards and then some pre-seed money as well. And then this year we also went to Davos. We just finished our trip to Davos. We presented in the one of the events during the World Economic Forum. And then a lot of people are very interested in learning more about water technologies today. So we see a lot of attention that's actually drawing into the space of plastic pollution and just water treatment in general. So we are very happy that we catch the trend, and we are very happy that we're one of the groups that are making some innovations in the space. Okay, so that's my presentation. Very, very honored to be here today with you guys, and I'm happy to answer any questions you may have.
So we get microphones out. I see hands up already. If you are online, we'll monitor either the chat or use the raise hand feature, and we'll try to call on you if you're online. And I'm looking for where the microphones are right now. I see you, Didi, but where's the microphone? Oh, there we go. See it right in the back.
Yes, you said that you clean the filters?
Yes. So we have
Just repeat it.
How do we clean the filters?
Yes.
Yes, we have two giant cleaning tank on the site. So the system was actually designed in a modular way. So we have 6 trays per array. You see that, 6 trays. And we move one of the trays out and we put it into the cleaning tank, and that vibrates it. That takes off around 92% of the plastic that we collected, and that goes through like another concentration process to collect all the microplastic from that cleaning tank. And after the wash, the filter are back to operation.
And then what do you do with the microplastics that you've collected? Where do they go?
That's a great question. You see our team size, and there's an advisor, and he actually is innovating a enzyme that aids microplastic, that kind of converts microplastic into another useful chemical. And he is currently making some progress on virgin microplastic and he's requiring more field sample that's like more degraded microplastic. So we are about to send our collected samples to his lab to see how we can turn this upcycling practice at a bigger scale.
So you're trying to look for useful things to do with the waste product.
I would say so, but it's not at a big volume. The whole idea is not we're gonna make so much money from like turning smaller, like few kilos of microplastic in mass into something that's like super valuable, but it's the idea of removing them from the water and then converting them to something else so they can no longer go back.
Because otherwise the waste product would be a burden you have to take care of.
Yeah.
Thank you.
Right over there to your left.
Yes.
Hi. You had mentioned that you collect about like 600,000 particles per wash cycle. I was
Yes.
wondering if you have any data about how much of a impact you've had on like the quality of the drinking water. So like what was the percent of decrease in microplastics in like the water coming out of the reservoir system?
That's a great question. We currently do not have that data at the moment. The reason is the inflow and outflow of the entire plant was very far away. So there are a lot of interfering locations that we don't know what will happen, whether the inflow data we're taking actually reflects the actual inflow and outflow. So an over-analysis protocol is not like by mass, but it's actually by quantification, so that we cannot know from a mass reduction perspective how much percentage of the microplastic was reduced from the inflow. But the next stage, we want to take multiple samples at different inflow locations to see how maybe different process will have different levels of microplastic, and after our system, how much of that has been reduced. Yes. Oh.
Yes. Is this on now? Yeah. Thank you very much. It was really fascinating to hear how you are approaching the problem. It sounds like right now you're looking at cleaning up the mess that we have made in the world so far and continue to make. Scaling down. Can I get one of these for my house? Both inputs and outputs, so that I'm not drinking microplastic when I drink water in my house?
We don't have any system for home use at the moment, but you can already use most of the RO systems for home to get rid of microplastic. The reason we choose to interfere at the larger facilities because we believe that's a bigger emission
Bigger
point.
impact.
Yeah,
Mhm.
yeah.
And how does the water temperature, like the oceans are getting warmer or the Arctic Ocean is frozen or not frozen, how does that affect?
Temperature does not really
Temperature doesn't matter to
doesn't
this.
really
Okay.
impact the performance of our system. Yeah, and if you are curious about your water, you want to, right? If you are thinking about how much microplastic are there in your water, we also have like water analysis services. Like we can do advanced water analysis for any water source you submit to our lab.
Thank you very much for a very fascinating lecture. Two questions. Out of that bottle of water there, that you said there's microplastics in that bottle right there in front of you. How much of that plastic comes from the container itself versus how much was in the water previous?
Actually, a lot of that is from the container because to make this kind of water, they would already have gone through ROs and even more fine filtration system. The reason that the final product still has plastic is largely because the container and then the UV degradation that makes the bottle shed even more.
Okay, thank you. And one more thing. You said 580 million microplastic, I guess, particles per year
Yeah.
was the number you quoted. In terms of mass, how much would that weigh?
We do not have the mass number. That's hugely because the analysis method we have, it can only identify sizes and quantities. But we are trying to invest in a pyrolysis machine that can actually burn everything in the sample and tell us like percentage of different chemicals. That way we can know how much mass are there in one collected sample.
Thank you.
One question online from Doug Bowl. What's the life expectancy of each of these filters, and do they lose effectiveness over time? So what is the life expectancy of these silicone filters? Do they lose their effectiveness? Right.
Currently 6 months. So in our lab, we did stress testing, repeat use for 6 months. So we do recommend changing them after 6 months. After 6 months, those fibers can be unwinded, and then the fibers can be gone to a silicone recycling facility, which is in Fort Lee, very close to where we are.
Right here.
Is this on? Okay. Hi, I had a couple questions about the downstream cycle. I'm a plastics bioremediation researcher with enzyme stuff.
Wow.
And you mentioned that you're looking at developing an enzyme to break down plastics, and I've worked in that field for a while.
Yes.
And one of the big issues is you're getting a sample that's going to be highly mixed with the different types of plastic, and we've yet to come up with an enzyme that's actually able to handle multiple types. Usually you end up focusing on just one type, and there's a lot of issues in terms of how long that takes. Could you clarify what type of plastic you're focusing on for this enzyme?
Sure. It's not our enzyme. It's the advisor, his lab's enzyme. And then his one, I think, can handle the PET. I don't know if he had made any progress for other microplastics yet. And I don't know what would be ideal process, maybe separating plastic for different stages of the enzyme degradation. But that is something we do want to look into, but we do not have the volume of the microplastic yet to do that kind of preparation for his. But if you're doing the same space, maybe it's closer for us to talk about it afterwards.
That'd be good. I also had another follow-up on that.
Yeah.
When you have these plastics going through the system, what is the operating temperature of the system? Because if plastic is heated, it can release different chemicals that it's absorbed into the water.
Our system,
Yeah. Is it just whatever the ambient temperature is, or?
yeah, it's whatever the ambient temperature is. It does not create heat because it's very just passive.
Okay. Thank you very much. I enjoyed your talk.
Right there.
Okay.
Yeah, I was just curious, what do you define as a wash cycle?
A wash cycle is when one round is finished and then 6 trays are being up. But this entire thing was lifted up for a cleaning cycle, the entire washing of the entire 6 trays. So let's say the water is very dirty, so we decide to do the cleaning, like alteration for 3 times a day. So that will be 3 washing cycles.
Over to your right. I'll just point out, okay, there's hands in the middle. I kept on going left, right, left, right. We got middle, right over here to the right.
My understanding is the filter you are using now is more like a mechanical, right? Mechanical filter. Do you ever consider using electromagnetic, more like a filter, static, or even better, probably a magnetic field approach to improve the filter performance?
I do think that's a very interesting direction to go through. We haven't charged the filter to create any of the magnetic
because
effects yet.
existing air conditioning system already have electrostatic approach filter. So I'm thinking maybe additional magnetic approach. You don't have to just depend on a mechanical device.
I do think that's a very interesting direction. So one thing we did consider is because it's going into the water, so how to create a magnetic field for the individual filters on top, integrated with the tray, would be a systematic electronic problem for us to solve. But I do think that's an interesting direction to take off.
What is your plan? Like, are you guys gonna bring this to like other countries, and also for places that don't have like water treatment facilities? What is your plan for like getting microplastics out of like that water?
We do have plans to to utilize the system internationally. The idea is to have many of those systems capturing at water treatment process after the secondary when they do not have the advanced. I don't think this will be a solution for large-scale drinking water because if there is a drinking water treatment facility, they already have most of the RO systems inbuilt. And for like remote drinking water treatment, you need more than just the microplastic removal for that as well. But we are actually working with a desalination company at the moment. So we are integrating our filters into their system. So as one of their process. So maybe there's opportunity to integrate with other more advanced RO systems as part of their treatment.
Online, how did you figure out that silicone doesn't break down like other plastics?
Because silicone is a different compound and it does not degrade endlessly, like into smaller particles under the UV.
In the middle, right in the back.
Yes.
Okay. I was wondering if you could have multiple arrays down at once in order to filter out more microplastics, or is it that the first array gets everything that can be gotten by the system?
We currently have a few rows. So this entire tray does not have just one row, it has multiple. So we zigzag it, it's already having multiple layers of that. Depends on how dirty the water is. And we can also increase the cleaning frequency to make it less saturated. But from our current experimentation, the ones that are in contact with the water the first two layers tend to have more microplastic. So there's a point when like the performance do not need to be that many layers of filters to make it function.
Something I was thinking is because you mentioned that the microplastics tend to float to the top, might it make sense to have a row ways behind the first few rows? That way, the top level water will be less concentrated with microplastics, and the ones that were below will float up into this second system.
I think when water goes to where we are, most particles are already like find
Okay.
their locations in the water column. So it's not the second wave of microplastic gonna wait the first wave of microplastic to be collected first and it will flow up. As long as their densities are the same, they all tend to be at a similar level in the water column.
Okay. Thank you.
Someone online asked if you could just repeat one more time, how does it even work in the first place? Why are microplastics attracted to the artificial roots?
Yes, because the material is hydrophobic. Microplastic, most of them are also hydrophobic. So when the two hydrophobic things interact in the water, they tend to stick to each other.
Right over here.
Hi, now this is again on the floating part of it. So you mentioned that most of the microplastics float. So, and this is not at the system level, but at an end user consumer level. So if I'm drinking from a bottle of water, what would be the effect if I could tap into the water from the bottom of the bottle? And you see, yeah, because practically we do have to drink from a bottle at times. So how much of the pollutants is reduced if you're drinking from the bottom of the bottle? And can, like, for instance, just flipping the bottle upside down and having a valve there reduce the end user impact?
That's a very niche question. That's a very niche question. I don't know. Like, my understanding is like the contact is not just like gonna be there, but like you constantly even the bottle, like the bottom are also contacting with the plastic bottle. So I don't know how quickly they emit and they separate into the into the top layer. I don't know.
There's a question over to your right, about halfway up.
Yes.
Yeah, first of all, I want to thank you for your great effort to, try to solve the, plastic pollution problems and the great presentation. My question is that because you see the system is passive, right? So
Yeah.
you put into the water, and let's say large area of water, body of water, and I guess what is the exact mechanism? I mean, I understand that there's a hydrophobic probably gonna attract those microplastic, but probably there's a capacity issue. And also, I mean, the microplastic far away from your system, how things are, get being collected, and do you require some like I don't know, water flow or something? And
So in the outflow area, the water are constantly being pumped out from the pump house. So that creates in enough velocity we need for the water flow to pass through the system. And the capacity is currently saturating around 6,500 microplastics, not nanoplastic. We don't know about the nanoplastic scale. So understanding that, we know how quickly we need to change the filters or wash the filters.
Right in the middle.
Yeah.
Yes.
Hi.
Yeah.
Thank you for filtering all this, but how do we stop this microplastic going into the system? Like, should we, get a better plastic bottle or avoid totally the plastic bottles? And, how do we stop these microplastics getting into the water bodies?
Many sources that microplastic are entering the water. For example, laundry. Like most of our clothing contains some type of plastic, and when they're washed, they're one of the sources that enter the water. And tires, when you drive, those tires are made of plastic compound materials, and those very small fragments will be washed by the rains and go into the water. Unless you change how all of us are living here, I don't think we can just end all of the source at once.
We have time for two more. So in the back.
Yes.
Thank you. But a question about scale. So the waste treatment plants that you're working with, like what percentage of the microplastics are actually coming out with the solids that they're, treating?
I don't know.
Okay.
Yeah, I really don't know. So in the primary treatment, the TSS, the sediments already been going into their sludge. And I do know there are a lot of microplastic in there already. But so before we start the whole thing, we actually did analysis at their outflow to see whether there are still microplastic coming out. We found between 20 to a few hundred microplastic per liter of water. So for some reason, those are still escaping the existing treatment. But by how much percent, we're not sure.
Thank you.
And then to your left, right there.
I remember you mentioning about how the washing process requires like vibrating and then taking out the microplastics. I was wondering if this cleaning process is like resource or energy costly or like heavy, and is the switch to making it all automatical, does that also help reduce like energy costs?
We're talking about the energy of maybe like a washing machine in comparison to like powering the whole plant. That kind of scale is compared to that scale, like a washing machine kind of power is not gonna cause a big issue for treatment plants.
If we could thank our speaker one more time. Thank you so much.